Augusto Getirana, is how you pronounce it. He's a research scientist at Goddard in the Hydrological Sciences Laboratory, and his research involves development, improvement, and application. Reading your LinkedIn profile of state-of-the-art computational models and integration of remote sensing for better understanding of spatial temporal variability of water availability and forecasting, including extreme hydrological events like droughts and floods and anthropogenic impacts on the water cycle. So he's the lead developer of HyMAP, which is the Hydrological Modeling and Analysis Platform, which is a global scale river routing scheme, and he contributes this to development of the NASA Land Information System, or LIS. So he's got a bunch of projects on global scale hydrological processes. He's also been awarded NASA's Agency Honor and NASA's Robert H. Goddard Honor Award for Scientific Achievements. Okay, so he got his PhD in hydrology from the Université de Toulouse, and also in civil engineering from the Federal University of Rio de Janeiro. So, and he was an NPP postdoc under Krista Peters-Ledard. So he's coming to help us out with hydrology here at GISS.
Oh, thank you. Thank you for the introduction. Yeah, so thanks for being here. Thanks for the invitation to come here at New York at GISS. So yes, today I will talk about some recent progress on flood modeling at NASA Goddard, which, I mean, it may be biased because that'll be my work and the work that I'm involved in. But there's no much, I mean, I think I'll be aware of other flood modeling developments going on at Goddard, if there was any. So these developments they vary from pure model development, basic model development to capacity building. Now I'll show some examples here. But like first, why should we care about flood modeling? And well, before I proceed, I'd like to let you know that I'll be using like flood modeling, river modeling, surface water modeling, and river routing schemes as the same thing. So they'll just refer to them. They'll be the same, the different names but it will be for the same thing. So to answer this question, let's take a step back and look at the bigger picture. Okay, so we know that the climate change and human activities have been magnifying the occurrence, intensity, and impacts of extreme hydrological events, and that's evidenced by all these major floods occurring in different parts of the world the past couple of years, being like more and more frequent. So here I'm showing some examples of flooding that took place in 2023 in Bangladesh and India, also Pakistan. I don't know if you remember that, thousands of people were displaced and were impacted by the flood. Charleston last year, that was December, in California as well last year. Just last week, there was another flooding in the Rio de Janeiro state in Brazil. So, yeah. So we have that I mean that kind of shows the importance of caring about flood modeling. And NASA in the past several decades, as we all know here, has been investing a lot in Earth observations through satellites, particularly water cycle components. So this is you've probably seen that this figure with this is kind of actually very up to date. It's from September 2023, showing the current water cycle fleet with existing on operation satellites and the planned for the next years. We even have here SWAT that was launched about 1 year ago. That's shown as operating. So the idea of the satellites is to kind of close the water cycle, and we're getting there, right? But there's still some limitations. So a clear advantage of satellites observing the water cycle is that we can monitor remote regions, so places where we don't have access to data. The spatial coverage, they're usually global, and it's open access for most cases. Like at least NASA data is open access. Some other space agencies, they also make data freely available. But there are also disadvantages, like the temporal resolution, like some satellites will be even monthly, like the GRACE data, the products that are available out there, they're monthly. Some people are trying to get the final resolution, spatial resolution, but yeah, we don't have the spatial resolution that many times is needed. For example, if you want to look at flash floods, you can't do that with the satellite data. Limited physical processes, so not all processes are represented. For example, groundwater, you don't have groundwater from satellite. So yeah, there are other solutions for that. A relatively short time series, like if you want to look at the climate, climate changes, the climatological scales, we can't with satellite data because you have like data for what, 20 years, and it can only look at past events. So, but if you integrate satellite data with computational models, you can through model evaluation or calibration or even data simulation, then you can compensate those disadvantages. As a result, we have estimates of unobserved physical processes, as I was mentioning, groundwater. If you get GRACE terrestrial water storage and assimilate into a model that can represent groundwater, then you can kind of correct or update or improve your model simulations of groundwater. We have a refined spatial and temporal resolution, so you get the best of both, the temporal resolution from a model and the spatial distribution from satellite data. And you can perform scenarios. You can just play around with what is, you can turn on and off things in your model, and also perform forecasts. So you can look at the future. So you can assimilate data up to the point where you have your initial conditions of your forecast, and then use that improved initial conditions to predict the future. And in terms of flood models, they can be characterized by some different characteristics. So I list here the spatial temporal scale. So some models will be more specialized at a finer scale or coarser scale. How it discretize your domain. So here I'm giving two examples. One is the MGB. That's a model that I used during my PhD, which is a vector-based model. And then HyMAP that I'll talk about today, which is a grid-based model. And the complexity of physical processes. Some models will be more, we have more processes represented than others. So just out of curiosity, this is the Nile River Basin, where I was testing, I was checking the impact of the operation of the Aswan Dam. That's Aswan Dam right here. So this is a naturalized system. This is the system with the reservoir operation. And right there is the impact, the isolated impact of the reservoir in terms of flooded fraction. And that's a list of existing models that you can find out there. Okay, so like focusing on HyMAP. So HyMAP is currently found in LIS. LIS is NASA's Land Information System, which is a very powerful modeling framework where you can find multiple land surface models, routing scheme. I think HyMAP, there's another one that was recently implemented. But the main capability of LIS, what makes it unique system, is the fact that you can assimilate almost any Earth observation data observed by NASA satellites and any other satellites in land surface models and routing schemes. So this is a schematic since HyMAP was implemented in LIS 12 years ago. All these black boxes show the new capabilities that have been added over time. So you have surface water data simulation over hydrology, the coastal interface, and so on. The green box is under implementation, so it's an interface between surfacing water and groundwater. And the red box is a future, like what is planned as future implementation. So there's lakes, water quality, and possibly energy balance. And it's also like it has a flexible spatial scale. So these are two examples: 1 degree global, and then the other one is a 200-meter spatial resolution at the very local scale. That's the municipality of Rio de Janeiro. So it can, so it's very flexible. You can just define your domain, the spatial resolution, and run the model. Over this past 12 years, several institutions across the globe started using, or I've been supporting them, either just as a support or in a funded project. So these are some examples, like there's K-Water in Korea, there's India, Thailand, and several in the US. The US Air Force is a major user of HyMAP within LIS. Some institutions in Brazil, Africa, and Belgium in Europe. And these are some examples of application environments that employ HyMAP within LIS. So I put 3 here. There's the Air Force, as I mentioned before, that it's called GHI, the Global Hydro Intelligence. The other one is it's under development right now. It's this new generation of the North American Land Data Simulation System, NLDAS. We are developing. Actually, it goes beyond the US. Now it goes this whole North America. And the food security LDAS, which is supported by NASA and the State Department, which is the Famine Early Warning System Network. So the content of this seminar. So I'll first talk about this work that was developed a few years ago. That the title is Rivers and Floodplains as Key Components of the Terrestrial Water Storage Variability. We'll get there. And the second one is the climate and human impacts on flood risk in Southern Louisiana. So this first one is a global scale study. Then you go for a more regional scale. And the third one is the development of a flood model for the city of Rio de Janeiro in Brazil, which is a local, even finer scale. And then I'll talk about the final consideration of prospects. So going to the first study. So that was a study that was published in Geophysical Research Letters back in 2017. So it's a kind of getting old now, but it's still very highly relevant. So the science questions that we tried to answer here was, what is the global impact of surface water storage on the terrestrial water storage, or TWS? And how does that impact vary spatially? So basically, the main motivation behind this is that I was seeing a lot of papers assuming that TWS from GRACE could be represented by, groundwater and soil and snow, and most, like all cases, they would just neglect surface water. So that's wrong, especially in like wet areas where, like the Amazon, you have a big surface water variability. So I wanted to quantify this and show people that, okay, what you're doing is wrong. So to answer these questions, we designed this methodology that represents terrestrial water storage using LIS with these 2 models. The NOAA multi-physics land surface model that represents the groundwater and the 4 layers of soil moisture and snow, and that simulates the vertical fluxes of water and energy, and also the water storages in these different components. And NOMP is coupled with HyMAP that simulates the horizontal water fluxes. So on one side you have the water storage in the groundwater, soil moisture, and snow, and the other you have the water storage on the surface in terms of rivers and floodplains. So those simulations were performed at the 1 degree globally using 12 different methodological forcings or combinations of these methodological forcings to create this ensemble and determine, we were able to determine the uncertainty of methodological forcings. But these are the results in terms of surface water storage in millimeters. So what we found is that about 2,900 cubic kilometers of water is stored in rivers and floodplains. That's higher than previous studies where they show 2,000 cubic kilometers or 2,100 cubic kilometers. And about almost 1/3 of that water is concentrated in the Amazon, or 800 cubic kilometers. And the uncertainty due to methodological forces is about 6%. And this is the animation Let me go back to get the animation again. Oh, animation's over.
So are we talking here
okay.
about just liquid water
Oh,
or
that's good. I'm sorry?
just a quick question, is it only liquid water or also like glaciers?
Oh, this is this is liquid water
Yeah.
in rivers and floodplains.
Mhm.
Yeah, and then so this is the HyMAP output, and this is NOAA NP output. So we have soil moisture, variability, snow water equivalent, SWE, variability, and groundwater storage variability. So if you put
So surface water, sorry, did I hear that wrong? 1/3 of global surface water is in the Amazon basin?
yeah,
Is that the statistic you said?
20%, almost 1/3.
When you say, can you define surface water again?
Is there water stored in rivers and floodplains?
So down to a
But
certain
not
depth,
lakes.
or to a certain depth, or just above the soil surface, or what do you?
Yeah, above the surface. Yeah,
Okay,
above the,
above,
yeah.
okay.
And that
Uh,
doesn't include lakes.
That doesn't include, lakes is not properly representing the model.
Okay,
Oh,
okay, okay.
Yeah.
in
Okay,
rivers,
got
and-
it, got it.
okay.
So like Caspian Lake, I guess.
Yeah, it's not there.
Yeah.
Yeah, that could, yeah, this would change the result. Yeah.
Okay, that makes more sense.
Yeah.
Mhm.
Got it.
Yeah.
Yes.
Okay.
And then when you combine all these four components, then you have the terrestrial water storage that is measured by or estimated with GRACE data. And then when you get those spatial temporal distributions of those different components, we can calculate their impact on terrestrial water storage. So we found that surface water storage has about 8% of the impacts in 8% on TWS globally. That's the global average. But as you can see here, that impact vary largely. You can see that most in the tropics we have a higher impact. In the Amazon, it's mostly you can even see the rivers in the Amazon. So it's so the terrestrial water storage in those regions are highly dominated by surface water storage. And then here in the bottom you have groundwater storage dominating by 17%, SWE by 22%, mostly in the high latitudes. And that's why moisture that dominates, I think on average globally, most of the TWS signal. And then if you look at more regionally, so these are the climatologies for some major basins. So you can see that, for example, in the Amazon, so surface water storage, the blue color is actually, it's surface water is I think that this is wrong. This should be, blue should be surface water and red should be groundwater, right? So in the Amazon, we have about 20% of TWS dominated by surface water. In the Nile, even though it's it's not in the tropics, but it's flowing in the desert. So there's no other water varying over time there. It's just dry. So just have the river. So the river dominates the terrestrial water storage in the basin here. And then from that dominance to lower ones, for example, in the Mississippi, you have 7%. In the Lena River basin is about 10%. All right, so this is the first study case that I'm presenting with the HyMAP. So let's move to the second one. That's more regional over Southern Louisiana. So this study was developed in the framework of this new NASA initiative. I mean, news that it's been 2 years. It's called the Earth Information System, EIS. And EIS has one of the main objectives is to promote open science. So we've been developing different studies and like tools using NASA data and make all these things available, all the tools that are developed available for people to either reproduce what we did or replicate what we did to their own cases. So the pilot study so we have a thematic area called sea level change and coastal risk. So that the topic, the pilot study for that thematic area was the Louisiana, sorry, was Southern Louisiana, the Mississippi River Delta. Why? Because these areas are highly impacted by human activities and also climate change. You have, for example, if you look at those time series here, the first one on top is a stream flow. So this is the inflow from the Red River, Mississippi River combined. So you can see there's an increase in the peak flows in recent years. There's also an increase in the sea level. You can see the clear sea level rise. In the past 20 years, there's an average increase of 5.1 millimeters annually. The wastewater storage from Grace also increasing, and we observed a coastal land loss over time since 1988. So the main challenge here is to how we can represent those processes in the modeling system with a hydrology perspective. So there were a few modifications that I made in HyMAP. So there was an inclusion of water management to represent, because these areas highly managed by the U.S. Army Corps of Engineers. So you have all these water transfers to protect, cities downstream like New Orleans and Lafayette. So there are three major diversions that were represented in the model using observations available on the U.S. Army Corps of Engineers website, and also the interface with the ocean. So that interface is basically we use sea level from rate altimetry as the downstream boundary condition of the model. So if you have a higher ocean level, so that the water will back in the river, so that will cause some additional flooding on the coasts. So in order to isolate the impacts of these major factors that we assume as relevant, so they are hydrology, water management, and sea level rise, we created three scenarios. So each of these columns in the table, they represent hydrology, sea level, and water management. So all of them have the hydrology, of course. Sea level, so we use here the 7-day time step rate altimetry data, and water management. So the first scenario has all the three factors. The second one has hydrology and sea level and remove water management. Third one, hydrology, instead of the sea level variability, we use the climatology, as there was no sea level rise and no water management either. And the fourth one, just hydrology with a constant sea level and no water management.
Can I ask a question? So in this river geometry parameterization, you can really see state outlines. It looks like Georgia has high resolution, Louisiana looks somewhat lower. Is that?
These are data made available by USGS. I think those gauges, maybe some states have more funding to have a better distribution of gauges. Yeah, that I just downloaded the whole USGS database, and that's the result.
So it's not like watershed concentration, it's actually by political boundaries.
Yeah, I mean, that's what it looks like, right?
And you can see, you can see Virginia, and then North Carolina, no measurements, South Carolina, Georgia, a lot of measurements.
So I use that to better determine the river geometry, river depth and width. So I used this point-based observations, and then I interpolated over between points. Yeah, so these are the results. That's from a scenario one, the complete scenario with the three factors combined. So the figure on the top left shows that the flooded area, so the additional flooded area from an early period, 1993 to 97, to this late period, 2016 to 2020. So you can see there's a general increase in flooded areas, mostly on the coast, but sometimes more inland. In the bottom left, there's the changing surface water elevation. So you can see that the water kind of went up, depending on more in some areas than others. On the right, we have the annual change in flooded areas and the annual change in surface water storage. You can see there's a general trend within this 30-year period, but that trend kind of increases in more recent years, in the past 2 decades, which is in agreement with the observations that I showed in the previous slide. And now, if you get those 4 scenarios, and it should be tracked one by the other, or a late period to be tracked by the early period, you can isolate the impacts of climate-induced hydrological change, or CHC, sea level rise, and water management. So you can see that by far, the hydrological change has a higher impact compared to the other 2. Actually, sea level rise doesn't have such a big impact, but we have to keep in mind that storm surges and tides are not included here. So, like that added to sea level rise, then that's when you have all those floodings caused by by the ocean. But and then when you overlap these maps, these flood maps, with cropland maps and population maps, then you can see the cropland population that is exposed to flooding. So you can see that the amount of cropland exposed to flooding due to sea level rise, as well as for population. Basically, we can see that hydrological change is like a major component, a major factor that should be accounted for when you're talking about coastal flood risk. And then we can also see that the water management is doing its job. It's protecting both cropland and population, right? So especially here the blue bar is a medium flood, like a flood that happens like half of the time, and the red bar corresponds to an annual event, an event that happens once a year. So more extreme, so more people and cropland being protected. Okay, so some things that should be, as I mentioned before, there's no inclusion of storm surges or tides, so there's more room for the improvement, which was actually implemented when this work was we continued to work on this, but instead of the Mississippi, we went to the Bay of Bengal, mostly Bangladesh, where vertical motion and irrigation or other factors were included in this in the system. And now we're moving back to the coast, the whole U.S. coasts, where tides and storm surges will also be accounted for. I have some extra slides after the presentation, so if anybody wants to hear more about it, I can show. So the third study case is at a finer scale, basically a local scale. So this is a study that has been developed in the framework of this unique partnership between NASA and a municipality. So in this case, the Rio de Janeiro. So the main goal of this partnership, signed in 2015, was to better understand, anticipate, and monitor disasters in urban areas, particularly for the city of Rio de Janeiro. And initially, the studies were focusing on landslides, extreme precipitation, and sea level rise, and all the disasters related to these processes. But then, 5 years ago, was 2019, we started considering the inclusion or the development of this flood monitoring system based on GISS and HyMAP. So the main goal here of this development is to transfer for operations this operational customized flood monitoring system based on NASA tools, models, and data sets, local expertise and monitoring capabilities, and capacity building. So we've been working very closely with the local partners. So we are getting their local experience and all the data that they measure in order to customize this model. So the challenge here was to get a model that it was built to represent rivers and floodplains and now we have to represent, water flow on streets. So with the, then we have the water intake, the on the water drainage system. So a full new module was developed to represent urban hydrology. So these are some schematic of how the drainage system was implemented. So here you have like a grid cell represented by, for example, 4 blocks, and then I use like average numbers of gutters, what the height of the sidewalk should be. So basically, the river was replaced by this gutter here. So this is the river, and then when it reaches a certain elevation, then instead of a floodplain, then you have the street and the sidewalks. Yeah, and then at the same time, the water is being, is flowing to the underground storm drain system, and that will so that we have basically two flows, water flows, one on the surface, the other one on the ground, and that underground flow will be dumped in the first river or lake in the region. In the tables, there's some the parameters that were used to define these processes. So this is one of the most severe floods in the city. So on the top left, we have hourly rainfall, and the bottom left there's the water depth above the baseline. Baseline was the first time step. So this is a water level above the first time step of that simulation. So you can see that there's flood everywhere. There's a lot of water. But and this is a 200-meter spatial resolution. So I developed this downscaling algorithm that uses fine resolution DEM. The DEM here is based on LiDAR. There was a 10-meter. Actually, the LiDAR data was like 8 points within a 1 square meter. But we upscaled to 10 meter because it was too much. It was too much data. We didn't need that. So from HyMAP outputs, we got to a 10-meter resolution flood extent, and that's the result for this region. So you can see the flood at the street level, right? I mean, it's hard to kind of validate this. We don't have data to tell what is. I mean, I think the validation of this model will be mostly based on crowdsourcing. Like people inform you that it actually flooded here the day that the model showed that it flooded. So there's a paper that came out in December fully describing the model, and I'm finalizing the package that will be transferred to the system for operations. Because of some limitations in accessing their server, I have to get everything like as final as possible. So somebody else will install the system without me seeing what's going on. So there has to be something very clean, and that's why it's taking longer than expected. Final considerations and prospects for HyMAP. So as I mentioned before, HyMAP has been substantially improved in the past 12 years since its initial implementation in LIS. And it's ongoing. There's always more stuff to be added. There's always people looking for collaborations to customize the model to their study cases. And the combination of all these capabilities put HyMAP as one of the most advanced global flood models available. I mean, there are others, right? Of course, but if you put all those capabilities that I mentioned before, you won't find the one with so many options. And ongoing and future development. So as I mentioned, there's the surface water groundwater interface that's being led by Tim Lemmers. That's a colleague at Goddard. We're also working on the SWOT data simulation. So SWOT is out there, was launched in December 2022. And some data is already available. So we are trying to catch up on these on other people, other labs, other teams are working on SWOT-DA. So we have to have that in LIS and HyMAP as well. So those systems that I showed, like GHI and the FuseNet, LDAS, they will be very interested in having SWOT data simulation so for unimproved stream flow estimates. And other things that are for more in the future, that is the improved representation of operation scheme. I didn't talk about reservoir operation, but there's a reservoir operation module that is it depends on the availability of water level observation. So the scheme that I want to implement won't depend on any kind of observation. So we just assume some generic operations as a function of the reservoir shape and other things. Inclusion of natural lakes and water quality module is another thing that's under the radar. So HyMAP is freely available in LIS through GitHub. So anybody who is interested in looking at the code and use it can have access through that link. And of course, new collaborations is always welcome, either for new developments and applications. So with that, I'd like to thank you for your attention. And I'm looking for.
Thank you. Still, any questions, or can you see any questions
I'll
online in
monitor
the
the
chat?
chat.
Okay,
Yeah, we definitely have a lot of time for questions.
okay. Could you,
There aren't any in the chat right now.
aren't any in the chat
Yeah,
right
but I'll
now?
let you know.
Okay, so let's see, that was cool. Any questions? I have a question. So, so LIS is, so, you're doing rivers and floodplains, and then you also have interface with the NOAA soil. So they're like separate components that are coupled together, and is that correct?
Yeah, so
Yeah.
these are two independent models that we try to couple them
Mhm.
within LIS.
Okay.
There's the two-way coupling that was developed a few years ago. So basically we informed the land model. That's what we were talking earlier.
Yeah,
So inform the land model with the water extent in HyMAP and the water availability. So based on those two, water extent and availability, we basically make that water available for infiltration and evaporation on the land surface model side.
okay.
And then there's this back and forth. Every time step, the land model will provide HyMAP with a surface runoff and base flow, and HyMAP will go back to the land model with water availability in the surface.
And how do you decide to partition runoff to the soil versus to lakes, and the lakes don't exist right now, right? In the
Yeah, so you just have surface water. Yeah, so the lake, if your topography shows a hole
Mhm.
in the land, so a lake will form there naturally, because the HyMAP uses this local inertia formulation, which is a simplification of the San-Venant equations, which is a simplification of the Navier-Stokes equations that allows us to represent backwater effect. So whatever happens downstream may impact upstream of the river. So if you have a hole, so instead of the water flowing downstream, flow upstream. So the water, that hole will be filling with water until it reaches the surface, and then finding the nearest exit. So that's how lakes are represented in HyMAP as like super full rivers, like rivers that are overfilled.
Okay.
Yeah.
Cool, we'll go into that some more in the discussion.
I'm
Anybody-
surprised you don't apply it to Miami. I mean, just Miami isn't that underwater like frequently.
Yeah, so Miami is in the domain for this U.S. coast work, so
Yeah.
we'll be there.
Okay.
Yeah, so the Miami, Houston, New York, we'll be able to see. So the idea for this new project is to look at projection. So look at how all these factors combined, tides, storm surges, sea level rise, hydrology, vertical and motion, how they impact individually and combined the how they impact in the past and how they will be impacting the coast in the future.
Also ocean tides.
Yeah,
I mean,
tides, yeah. Mhm.
What's the variation in ocean tides like in New York City? Maybe, you know?
That
I don't
just
know.
under 1.5 meters or so.
Yeah,
I
it's like
see.
quite a few feet.
Okay,
Sometimes it can be a little bigger than that.
yeah,
Yeah.
anyway, that's,
Yeah, I'm not an oceanographer. I just use that as a boundary condition in my model.
So kind of along the same lines of that question, when you're looking forward, projecting at these cities, are you interested in also looking at different types of urban planning and water management? Because presumably most of these coastal cities will try to build some kind of resilience against floods.
Yeah. So that's some slides that they didn't make it to the main presentation.
New York
Yeah.
City, they want to build basketball courts to be impromptu reservoirs sometimes.
Really?
Basketball courts.
Yes.
It's interesting.
So as part of the study, the flood monitoring system in Rio, so we overlap the flooded areas with the population maps. So we look at the impacts of, so these are three different experiments, one with a no drainage system at all, one with an optimal drainage system, and another one with a more constrained drainage system. So each row here represents a level, like a water depth. So above 10 centimeters, above 25 centimeters, above a half a meter, and above 1 meter. Like so, like, when you go down, you have more severe flooding. So you can see the population that is more exposed to more severe floods. And then I mean that can be used to city planning and management. And something similar that we did was using the minority population map and this normalized household income. So we did the same thing. So we can see for different flood severities, we can see how the income and the minority population changes over time. So basically, if you look at these two rows here, for these minorities and the income. So the more severe the flood is, more minorities are being impacted. And the more severe the flood is, the lower the income is. Which I mean, it's kind of intuitive for some people, like but now it's proven with numbers. So now we have the model to actually give numbers to those intuitions. Yeah.
I think it like was Manu Lal, maybe somebody in his group did a study where New York City, like poor neighborhoods were flooding more and had like they correlated it to sanitation trash complaints, and there's a high level of correlation, meaning that the drainage systems operate like subpar
Yeah.
in poor neighborhoods compared to
Yeah,
wealthy
that's
ones.
complicated to represent in the model because we don't know where is the drainage system is clogged with trash. So in the case of Rio, just assume an average dimension for the pipes. But if you have that information, you can just replace the map with the actual drainage system.
Interesting. Sorry, Mohammed had a question.
Thank you so much. It was very good. Let's assume we have a precipitation, so we should first determine the budget of the interceptions and then soil moisture and then surface water, which gonna be on marsh on grid to get to the river and then routing on the river, if I'm not mistaken. So, for example, you compare with NOAA and P, which has WAR Hydro has a very decent documentation. My first question is there any documentation about the models that you guys use in this specific framework?
The models used here in the three cases that I presented are NOMP and HyMAP. Yeah, I mean, the HyMAP, there's several papers. There's no like technical report or manual, but there's several papers describing all new implementations, developments. There's a paper describing them. And NOMP is it's well known.
Regarding the channel representations, NOAA and P consider very simple trapezoidal and then, for example, rectangle for floodplain. So for bankable, it's trapezoidal, and for floodplain, it's very simple
Yeah.
rectangle.
So you're talking about the routing scheme in World Hydro, right? It's no EP doesn't have a routing scheme, no EP is just the lane model.
So after you get to the river, to do routing, they consider such a boundary conditions for routing to make it simpler. My question is how you guys do that? You know, how you represent your channel geometry in
Yeah, so that's a good question that I skipped that part. So for the Southern Louisiana work, as there were those maps. Hold on. Let's see. Here. So for this case, for the US, we have like tens of thousands of US GS gauges measuring river width and depth. So that's what I use to generate the river geometry across the US. Elsewhere, global applications, I use empirical equations that estimate river width and depth as a function of the drainage area. So the larger the drainage area, the larger the river geometry will be. And then not only that, it's also a function of climate regions. So like the equation will change from a continent to another, from a basin to another. Yeah, but yeah, I mean, globally, it's hard to quantify that precisely. So you have to generalize in some sort of equation.
It seemed like better to do it based on the like monthly or annual river flow as opposed to the drainage area. Since the amount of water going through would be more.
Yeah, that's another way to. Some people use equations as a function of stream flow. Yeah, but I mean, just can pick one.
Could you use that instead of these measurements for the US?
I
well
prefer
do
to
you
use
do?
the actual measurement.
No, I know, but
okay.
it's a way to vet your estimate. These
I mean,
measurements.
that's outside the US, the
Like you-
formula for outside the
Use
US.
your formula in the US where you have observations and then like this way works better.
Yeah,
than
but
that
the
one.
things that like the question that you get for the Mississippi, for example, may not be the right equation for the Amazon. That they have very different dynamics. The river have dynamics. The basin they have different climates, so it doesn't really apply. That's for example the mean stream flow in the Amazon is 200 cubic meters per second. 200,000. And Mississippi is what 20, 15 something. So it's different scale. So you can really extrapolate. I could validate the equations that I have globally over the US using those, but I can't.
Yes, that's what I mean.
Okay. I thought you were talking the way around. To use to get equations from that and extrapolate. Oh yeah, that's right. Yeah. Never mind. That's a good idea. Yeah, I haven't thought about it, but yeah, it can be done.
Then you could test, like, is it better to look at river flow or is it better to look at drainage surface area? See which one works better.
But then the
Or
equations,
different regimes, one works.
yeah,
better than the
but
other.
the equations they also you can kind of change the equation, like better calibrate. So for example, I use a set of equations in HyMAP. So other models will have other developers will have slightly different equations also using drainage area. So yeah, so there are different ways there's no like unified way to do this.
So I ask another question because it's one of my studies that I'm working
Oh,
on.
go ahead.
How do you estimate the bankfold using USGS data? Because USGS data are just gonna give you the field measurements.
Yeah.
USGS agents gonna give you the width and then.
Yeah, I know. So I basically I use like I think the 95th percentile of the measure. So for each gauge you have multiple measurements. Yeah, so I kind of computed the I did a distribution and I got the 95th percentile. Yeah, that was like very
Wrong.
yeah.
Cool. But it's a common practice. I saw it in many studies. They
Yeah.
did the same.
Mm-hmm. Yeah, more questions?
Actually, could go back to your Amazon.
the global.
You said that's old, but it's still relevant. I mean, what, after you did that, what kind of other studies came out after this to evaluate, how, like, like maybe GCMs, their land models?
Yeah, people have been contacting me to get those outputs and,
Yeah.
and account for surface water in their studies.
Uh-huh.
Yeah, there's one person working at Ohio State University. He's a former PhD there,
Mhm.
and he was like estimating the water storage in river channels, neglecting floodplain just
Mhm.
from satellite data. And then he asked me to give him these outputs just as a form of, it's not even validation because that's a model output, but just to have like a benchmark.
Mhm.
Yeah, and I still see a lot of people not like still neglecting surface water
Mhm.
because they for example, like some regions of the world you can actually assume that you can neglect. In the Midwest,
Yeah.
we can neglect like many places in Australia, but others you just can't, like the Amazon and the Congo and other areas.
Are there some MIPS that this HyMAP's part of, you compare how different models?
Someone several years ago started this river model comparison, but
Okay.
didn't go. I don't know what happened. That there was no outcome from that. But that's a thing that should be definitely be done.
So there's like, for CMIP, there's, LUMIP, LS3 MIP, and I don't know if, I didn't participate in directly. I don't know if there may be an offline component for some of the, because there are a lot of land models that participate in this. I'm just curious. I have no idea how they perform with regard to this, so we can.
Yeah. I think it's mostly comparing stream flow because some models they won't compute like surface water storage or floodplain extent. They'll just compute stream flow.
Mhm.
So
Right.
you're basically comparing apples and oranges.
Right, I see. Okay.
Yeah.
So how this amounts actually are estimated? I mean, you cannot do it from satellite. I mean, GRACE probably wouldn't give you much because GRACE would give you only the change in the storage, but the total amounts
Of
of water, I mean, like in Amazon,
How do you evaluate
how
it?
much do you know?
yeah, that has to come from models because you
Usually only from models.
yeah.
Okay.
Well, satellites will give you the variability,
Mhm.
won't give you the absolute value.
Yeah, well, satellite, I guess, can give you the area, but flooded area, but you don't know how deep it is.
Yeah, you don't know you don't know the bottom of the river, but you can get the annual variability. So you know the lowest level and the highest level.
Yeah.
You know how it changes. You don't know how the absolute amount of water stored, or you know how much water the change in the storage
Yeah.
over time.
Yeah, but here you're talking about total amount of storage, not
Yeah.
variability.
Yeah.
So,
Yeah,
Basically,
I mean, with the
need to
model,
know,
you
I
can
guess,
estimate.
bathymetry of rivers and lakes. Which
What-
kind
what-
of
what-
difficult to get, I guess.
It's terrestrial.
Yeah,
Terrestrial water storage is like aquifers, but also like just soil water, so
it's
something
all the water in the
that percolates
column.
down. Does your model stop once it becomes soil water?
Uh,
Like, so is there like, does your model include soil water as part of its simulation?
Yeah, no MP, yeah, simulates.
I don't know.
like the water underneath rivers,
Yeah.
water underneath lakes.
So this is the no MP, the land surface model. So it's composed of 4 soil layers. So you have soil moisture in each of these layers, and they interact with each other.
And HyMAP is just,
Routing.
It's a separate model.
okay, oh, HyMAP is the surface routing.
Yeah.
And NoMP is what's inside each box.
Yeah, so
Sorry.
NoMP simulates the vertical water balance, the water
Okay.
fluxes and storages vertically. Yeah,
Mhm.
and then the output from NoMP, they are using HyMAP or surface runoff and base flow. The 2 fluxes that they are used as input in HyMAP.
Okay, so the dimensionality of rivers is solely from HyMAP routing water to NoMP in flooding areas? Is that what the rivers have a width and depth, but it's width and depth that's prescribed, it's given to NOAA or?
No, NOAA doesn't know that.
Okay,
NOAA is
so-
not aware of what's going on in HyMAP.
So HyMAP has dimensionality to rivers. though.
Yeah.
Okay, so
yeah.
it has an area and so rivers have an area.
Yes.
Okay,
Mhm.
and then but do you have subsurface water underneath your rivers?
Yeah,
Okay.
I mean,
Okay,
not in the way that this work was implemented. So
Okay.
because HyMAP is not communicating back to NOAA what is happening in the surface.
okay.
So I mean,
Okay.
if you do a two-way coupling, a full two-way coupling, when
Uh-huh.
you know when HyMAP informs back to NOAA what's going on the surface, then
Uh-huh.
you know, like the water, the surface will infiltrate the
Okay.
soil and you saturate the soil under the river.
Okay,
Yeah, but that capability wasn't developed back then.
okay.
Yeah.
And no MP has lakes then?
Um, I've seen the option for lakes in OMP. I don't know if the version that we have in GISS can simulate lakes.
We saw someone, Carrie, I can't remember her last name, like Jackie Osterman's postdoc gave a talk and it was like thinking about soil water versus like surface water. And it was like how much the water balance and like you had sophisticated topography and when the water balance was overly positive, those things would pop up above the surface wherever it may be. And then they became the lakes or the rivers or whatever.
Yeah, that's
It was kind of
the MP in the name, no MP, is for multi-physics. So there's a lot, like they went from this NOAA this traditional NOAA model to this NOMP where you can just pick different representations of all kinds of physical processes. So we either don't have all capabilities in GISS or they're just not activated because nobody saw the need to have them there. So I cannot answer that question.
So we have a follow-up or kind of adding to this discussion from Gavin, where he's asked, why have lakes been so neglected?
Why?
Why have lakes in all these modeling efforts been so neglected?
Because it requires some additional effort to have them included in. You need the bathymetry for these lakes. The HyMAP uses the topography from SRTM or some other product, global DEMs, and unless you have the hole in the inland that is the empty lake, it's you cannot represent the lakes in the model.
So then I have a question, without the lakes, does that not impact the simulation of stream flows and runoff?
It does, yeah, it
Okay.
does. Yeah,
So-
you have an impact. If you
Yeah,
have
okay.
if you're in a basin highly controlled by a lake,
Uh-huh,
like let's say the Nile, you have Tana Lake, you have Lake Victoria, you will have an impact. Like if you're not representing, for example,
Okay.
talking about carving the hole to represent the lake.
Mhm.
That's what we do with the rivers. So for the rivers are represented because you're carving the riverbed in the topography.
Mhm.
So that's the same thing that has to be done with the lakes. If you don't, otherwise you just have a flat surface. That's the lake, the top of the lake.
So
Yeah.
are we interested, Nancy, in borrowing NOAA MP to replace our land surface model or what?
I don't think so. I mean, we just can borrow concepts.
Right.
I mean, we can do, that's our strategy discussion. That's already discussed afterwards.
Well, we hit 2:05. I figured it
Oh.
was discussion time.
Oh, yeah, okay. Well, we're gonna have an hour discussion that starts at 2:30 if anybody. So we're gonna have, we're gonna have another hour discussion after 2:30. Yeah, so it'll be break out.
All right, in that case, I guess
Okay.
we can end the seminar officially.
Okay.
And therefore give a round of applause. Thank you so much.
Thank you.
Thank you. And is the discussion open to?
Yeah, definitely. So,
Mohammed, I didn't realize
Yeah.
that this was so closely aligned with your research.
Yeah,
We were
which-
remiss in not inviting you to hang out with us.
yeah, I didn't even know you existed. So, would you like to join us?